Hello everyone. In this video, we're gonna talk about descriptive statistics, but now we're gonna focus on metrics. So remember that descriptive statistics is used to summarize data. So far, we have used tables and plots, and now we will include metrics to be able to understand a dataset. All right, so the first key definition that we need to understand here is the difference between precision and accuracy. So what is the meaning of accuracy? Accuracy means be close to the target. So in this example, we have the red dot and we want to hit the red dots. So accuracy means that on average, we are able to hit the target. Therefore, in this example here, this is number 1, 2, 3, and 4. Then in 2 and 4 are the only two plots where we're hitting the target. So most of the observations are close to the red dot. So we're hitting the target. So that's accuracy, to hit the target. So in real life, accuracy means, for example, you are talking about, imagine a product such as like a bag of rice or beans. So those products in the label, you will find the average content. So a company will hit the target every time that the amount that it's supposed to have that product in the label, actually it's the one that it has in the bag. So that's the meaning of accuracy. Always when you hit the target, it's a centrality metric. It gives you an idea of position. On the other hand, it's related to dispersion. It's related to variability, like how widespread are your observations. So in the first plot, in the first one, if you notice, the observations have a lot of variability. They have a lot of dispersion, right? Now, if we check number 3 and number 4, please notice that the observations are clustered together. They're close to each other. So that means that they have high precision. They have low variability. So this is not a position metric. This precision refers to uncertainty, to how widespread are your observations. Okay, so in this unit, we will talk about central tendency metrics, such as the mean, median, mode. That's the focus of this video. And then in the remaining videos, we'll cover position metrics, variability, and shape metrics. So let's get started with the central tendency metrics. The most popular one is the mean. I'm pretty sure that at some point, most of you have measured the average with your grades or at any other, in different contexts. At some point, you measure the average of something. So what is the average? It's just the sum of observations, and then we divide that sum over the number of observations. That was going to give us the mean value. So we have a sample mean, population mean. So the difference here is that sample mean implies that we're using sample value or the measurements from a subset of the original population. So it's the complete picture. That measurement is based only in some individuals or objects because we're using a sample. Please notice that the notation matters here. If we're computing sample mean, then we're using X bar to represent the mean value. Now, if using the population information, that means that we're including the whole set. So if that's the case, then we use mu to represent the parameter of the population mean. But again, the question is pretty much the same. It's just the sum of the individual observations divided by the number of observations. So that's how we get the mean, which again, most of you know as the average value. So some of the properties of the mean, it is an equilibrium point. That means that if we measure the distance between each observation and the mean, and we add them together, then the difference is going to be equal to 0. So that's why we call it an equilibrium point. And let's check an example where we can verify that property. So here we're told that Anna made 4 payments. The numbers are 600, 650, 700, and 1050. So we're going to compute the mean, and then let's find the distance from each observation to the mean. So given these 4 values, if we find the average, remember that will be 600 plus 650 plus 700 plus 1050 divided by the number of observations 4. So we're going to the average value, which is 750. That's the average value. Now, if we start measuring the distance from each observation to the mean, so that'll be 600 minus 750. The distance is minus 150. So we keep going until the last one. 1050 minus 750. The distance of the difference is 300. So if we add them up, it is equal to 0. And that will always be the case if compute that distance and we add them together. So this example highlights that property. Also shows one weakness of the mean value. So please note here that most of the observations are below the mean value. There is only one observation that is above the mean value. So this, the problem is that the mean gets easily affected by extreme values. So if we have like a really high number or a very tiny small number, then those numbers, those extreme values, are going to affect the result of the mean value. So it gets easily affected by extreme values or outliers that we might have in our data set. So we got to be careful when we're analyzing the mean. We are either removing, or at least we know that we have to be aware if there are some extreme values or outliers in our data set. There are some possible solutions we will see in a couple of slides. So since we know that the mean is affected by extreme values, so one possibility is to trim some of the observations. We can compute the trim mean. If we do that, then we are like avoiding the influence of those extreme values. So we trim a mean. That means that, for example, if we said that, okay, let's compute the 10% trim mean, then we're gonna we have to arrange the observation from the smallest to the largest value, and then we're gonna remove 10% of the lowest value and 10% of the largest values. With the remaining observations, we find the mean. So in that way, we make sure that we are not being affected by extreme values if we know that there are some extreme values in our data set. So let's check this example. So we're told that some measurements were recorded from drying time in hours for a certain brand of latex paint. So we know there are in total 15 observations here. 3 times 5, 15 observations. So now let's answer the questions. The first one, it's what is the sample size of the above sample? So the sample size refers only to a number of observations. So there are 15 observations. That was an easy question. Then the question is asking, calculate the sample mean for the test for this data. Find the sample mean. So to compute the sample mean is just to add them up, all of them. So x bar is going to be equal to 3.4 plus 2.5 plus 4.8 until we add the whole table, plus 3 plus 4.8. And we divide it by the total number of observations. So you can compute that number divided by 15. And then in part C, it is asking to find the 20% trend mean for the above dataset. So if we have 15 observations, the 10% is 1.5, right? So 20% is going to be three observations. That means that we need to remove 3 of the lowest values and 3 of the largest values in our data set. That's the meaning of the trend mean. So let's identify what are the lowest values in this data set. So we're going to remove only 3 of them. That's 20% of the observations. So the 2.5 for sure is the lowest value. Then we have 2.8. So that will be the second value. And we have another 2.8. So that will be the third lowest value in our data set. So now we have to trim in the upper side the 3 largest values. So let's find first which is the maximum value in our data set. That will be the 5.6. Then what is the second largest value? That will be the 5.2. And we need to trim one more, remember, 20% below and 20% above. Then the next largest value is 4.8. So you remove only 3. Even though there's another 4.8, you don't have to remove it because we already have 3 observations, right? So we cannot just keep removing since we already defined that we're going to remove only 20% of the observations below and above. So once we're done with this part, then we just add the remaining observations. So that will be 3.4 plus 4.8. We keep going until the last values of the table that were not removed. That will be 4 plus 3. And in this case, changes, of course, because we have removed some observations. Since we removed 6 values, then we will only have 9 observations. That's how you will compute the trend value. To be honest, in this example, there are no like really big numbers, like extreme. So these 2 X bars, like the old information and the trim X bar, they will look pretty much, like close to each other. But imagine the case where we have a scenario where the maximum value is not 5.6. Imagine that the maximum value is 50, for example. So there's a huge difference between, like 5.6 and 50. So this is extreme value in this data set, right? It's far away from most of the observations. Then if we trim it, we will get rid of the 50. So that extreme value won't affect the X bar estimation. So if we have an extreme value, then the difference between the normal X bar and the trim X bar is gonna be huge, the difference. But again, here in the linear problem, we don't have like extreme value that will cause such a trouble. All right. So in addition to the mean, there are a couple of metrics that are useful. The mode. What is the mode? Is the most popular output. So that means that the mode is referred to the observation with the highest frequency. So if we're given a data set like this one, we need to find the frequency of each observation. So this is 6. For example, the number 6, we have it 3 times, right? 1, 2, 3. The value of 3, we have 2 3s. That's the frequency equal to 2. 9s, we have 2 9s, and 5 only 1s. So the observation here, or the value with the highest frequency, is 6, because the frequency is equal to 3. So how do you compute the mode? It's going to be the value with the highest frequency. And it is possible that you have multiple modes. So let's say that I expand this data set. So I add one more value. And let's say that the value that I add, it's a 3. So if we add a 3, then we have that the number 6 has 3 observations, but the value equal to 3 also has 3 observations. Then the mode in this case is going to be 6 and 3, because both of them have the same frequency, and that frequency is the highest in the data set. So it is possible to have multiple modes in a data set. All right, so the last central tendency metric that we're going to cover is the median. The median, it's the observation that splits your data set into equal parts. That means that above the median, you will have 50% of the observations, or below the median, you will have the remaining 50% of the observations. So there are some steps that are required to be performed before we compute the median. The first one will be that we require to arrange the observation from the smallest value to the largest value. So we're gonna make sure that we arrange the data set from the smallest to largest. And then there are two rules here. If the number of observations is odd, then the way we compute the median is just we will take the position, we will take the observation that is in the position n plus 1 divided by 2. So for example, let's say that n is equal to 51. So we have 51 observations, right? That's an odd number, an odd number. So how can we get the median? First, we arrange that data set with 51 observations from the smallest to the largest value. And then we need to locate this position, the position n plus 1 divided by 2. So if n is 51, then 51 plus 1 is 52, divided by 2, that will be 26. So we will go to the position 26, and the observation that is located in that position is going to be the median. That's, again, if n it's an odd number. However, if n is an even number, then the procedure is going to change a little bit. So if it's even, then what we do is that we compute an average. So we add the position that is in the observation that is in the position n divided by 2 plus the observation that is in the position n divided by 2 plus 1. We add them and then we divide it by 2. This is an average of two observations. And that's how we get the median. So let's practice and let's check these cases. So in the first one, in the first example, we're given 1, 2, 3, 4, 5 observations. 5 observations, right? So it's an odd number. So since it is an odd number, then the way to compute is that we go to the position n plus 1 divided by 2. So if n is equal to 5, then n plus 1 is 6 divided by 2, that's equal to 3. Therefore, the median is going to be the observation that is located in the third position. And if you notice, please check that 50% of the observations are below. There are 2 observations below, and there are 2 observations above the median. So it splits the data set in 2 equal parts. It splits the data set in 2 equal parts. So let's now practice both cases. In the first set, we're given let's check how many numbers. 1, 2, 3, 4, 5, 6. That's an even number. That's an even number. In n equal to 6, n equal to 6. In the second one, we have 1, 2, 3, 4, 5, 6, 7. N equal to 7. All right. So before we proceed, we need to make sure that we arrange the data set. Remember that that's the first step. Then for set 1, that will be 1, 3, 6, 8, 11, and 16. For set 2, that will be 1, 3, 6, 8, 11, 16, and 20, right? So now let's just perform the analysis for the first set. So the median for set 1. Remember the equation here? So to find it, since n is even, then we compute the average of two observations. The observation that are located in n divided by 2 and the observation that is located in n divided by 2 plus 1, so the next one. So n divided by 2 in this case is 3, so it's the third position. And n divided by 2 plus 1 is the next observation, right? The observation that is located in position 4. So now we just find the average of these two values, one plus the other divided by 2. So that's going to be 7. So the median of the first data set is 7. So 7, here is going to split the data set in 2 equal parts. There are 3 observations below and 3 observations above that value. Now, in the second data set, it's easier because the number of observations is an odd number, right? So since an odd number, then according to the equation, the median is going to be the observation located in the position n plus 1 divided by 2. So there are 7 observations, n plus 1, that's 8, divided by 2, that's 4. So the observation in the fourth position will be the median of the second data set, right? So the median is going to be equal to 8. And again, this observation splits the data set in 2 equal parts. So that at the beginning, I said that the median is not affected by extreme values. So let's check that quickly. Imagine that instead of 20, in this example, we have 200. Instead of 20, we have 200. If that's the case, please notice that again, the way in which you find the median is not affected by that extreme value, because the median again is going to be equal to 8, the observation located in the fourth position. So that's why the median is not affected by those extreme values, and it's a nice metric when we're analyzing centrality measurements. So this is it for in this video. In the next video, we're going to talk about position metrics, such as percentiles, quantiles, and deciles. So I'll see you on that video.